So we're talking about finite Galois extensions. A finite field extension K over F is called Galois if it is normal and separable. Normal means that K is a splitting field extension over F, meaning you obtain K by adding all roots of a bunch of polynomials. So if you take something in K, and if you take its minimal polynomial in Fx, all the roots of this minimal polynomial are available in K. And separable means that these minimal polynomials all have distinct roots. Okay. And there are two equivalent conditions that you can write down that tell you when some extension is Galois, some finite extension is Galois. Okay. In particular, this numerical condition, part B, will become crucial in the further development. So I have a bunch of lemmas here. These are basically bits and pieces of the fundamental theorem of Galois theory, you might say, or parts of the proof. So we are stating them first because they are important in their own right, and they will also pave the path towards the main proof of the main theorem. The first one down here on the left has essentially already been argued. Well, part of it anyway. If you have a tower of extension, F contained in M, contained in K, and the big extension is Galois, if the big extension is Galois, then the upper extension is also Galois. At least we have argued that if the big extension is normal, then the upper part is also normal. And we quoted the statement for separability. Well, at least if you're sticking to characteristic 0, then every finite extension is separable, so we won't worry about that. That's this lemma. Okay. So at least for extensions of Q, we are good. The second one says that if you take a Galois extension K over F with Galois group G, then the fixed field, remember this just means all things in K that are fixed by every element of G. That's just the base field. So the only things in the bigger field that are fixed by all the elements of the Galois group are the elements of the base field. Of course, by definition, the elements of the Galois group fix the base field. So it says that they don't fix anything more than that. Okay. And let's see why this is true. So this is rather interesting actually. So you take some A in K, G, and you want to show that A is actually in F. Right? You want to show that Kg is F. So you take something in Kg, you want to show that it's in F. What we would argue actually is that this extension is equal to F. So we'll show that these are equal by showing that the dimension of this vector space is 1. That seems a strange way of arguing, but that's what we'll do. And moreover, the dimension of this vector space is same as the number of embeddings of Fa in the algebraic closure fixing F. The separable degree, remember? We are in, the big extension is Galois, so it's separable. So this smaller extension is also the smaller extension is also separable. So if I can prove that the separable degree is 1, then I'll know that the degree is 1, then I'll know that this field is equal to that field, so I'll know that A is actually down here. It seems a very roundabout way of going about it. That's how this goes. So I want to show that this separable degree is 1. Meaning what? Meaning that any embedding of this FA into the algebraic closure is actually just the identity map. And why is that? So take sigma and embedding from FA to F bar whose restriction to F is identity. Maybe I should first say that take A in KG, right? And then take one of these embeddings. Then we know that it actually extends up here. Whenever you have algebraic extension and you have something algebraic closure, then any embedding can be extended. Then sigma extends to sigma 1 from K to F bar. But you see K is a splitting field extension over F, and this sigma 1 still fixes F. Since K over F is normal, but it's a splitting field extension, I know that any embedding into the algebraic closure is actually an automorphism. So sigma 1 is actually an automorphism of K over F. But that's the group that we are calling the Galois group. So sigma 1 is actually an element of this Galois group. But that tells you sigma 1 of A is A, because A by definition lives in K upper G, meaning it's fixed by all the elements of the Galois group. Since A is fixed by all elements of the Galois group, which means sigma fixes A, because sigma 1 after all extends sigma. So sigma 1 restricted down here is just sigma. So sigma A is A. But sigma fixes F, it also fixes A. This implies sigma is identity. So you're not doing anything at all. So the separable degree is 1, because any embedding is just the identity. So the degree is 1 since the extension is separable. So F equals FA, so A is in F, so KG is F. Okay. This is rather beautiful and clever, I suppose. Okay. The third one up here relates the conjugates and minimal polynomial with the Galois group. So here's what it says. You have a Galois extension and Galois group G. Then if you take an element in K and hit it with all the elements of the Galois group, the orbit of this element A under the Galois group is exactly the set of conjugates of A in F bar. And then if you name those conjugates A1 up to AR, maybe the first one is A, and then we have some other ones, then if you write this polynomial J equals 1 through R, x minus AJ, this polynomial to begin with has coefficients in some bigger field. These AJs to begin with only live in the algebraic closure, or at least in K. But this polynomial, I claim, actually lives in Fx. So the coefficients of this polynomial actually would end up being elements of F. In fact, this polynomial is the minimal polynomial of A. So in terms of the Galois group, you can write down the minimal polynomial just like this. It's product x minus AJ, where AJs form the orbit of A under the Galois group. So the result is rather important. Well, the proof is not bad. And the first part we know already, in fact. What I want you to just note is that G in this context is also same as the set of all embeddings of K in F bar fixing F pointwise. Any automorphism is of course an embedding. Conversely, if you take any embedding of K in F bar fixing F pointwise, because K over F is a Galois extension, it's a splitting field extension, so any such embedding is actually an automorphism of K. I keep on quoting this theorem over and over again. It's really the reason why we fuss so much about embeddings. So G is same as the set of all embeddings of K in F bar fixing F pointwise. But if you take the image of A under these embeddings, you exactly get the set of conjugates. We have seen that already. So if you take the image of A under all these elements of G, then you get all the conjugates. Well, that's part A. And part B actually uses the previous lemma. If you look at this polynomial, you apply any sigma in G. So this lives to begin with is in Kx, because all these conjugates are actually available in K, right? Because K is normal. So this actually lives, to begin with, lives in Kx. But if you apply it, any element of the Galois group to it, then what happens? Then you get sigma Aj. But the Aj form an orbit. So if you hit it by any element of the group, the orbit just gets permuted, meaning these conjugates of A just get permuted when you hit it by any element of the Galois group. So sigma A1 through sigma AR, this list is exactly the same as the list A1, A2, AR. Because that's just basic group theory, that if you take an orbit of an element, hit it with any group element, you just again get the same set of elements. So this polynomial is again just Px. That means all the coefficient of Px actually live in the fixed field. They are all fixed by the Galois group, but K upper G, we just proved, is F. So the coefficients all actually live in F. So in fact, Px has coefficients in F. But now, of course, P of A is 0, because A1 is already A. And if you substitute A1, you get 0. So A satisfies this polynomial, so the minimal polynomial divides P. But on the other hand, all the roots of P are just conjugates of A. So they are all distinct conjugates of A. So each root of P is a conjugate of A. So each of these factors are also factors of the minimal polynomial, because the factors of the roots of the minimal polynomial are exactly these conjugates. So P divides P sub A. So P is P sub A. Okay, so that's why this thing is the minimal polynomial of A.